Hey everyone, how's everyone doing? Hope you're all doing well. Welcome. This will be part of a mini series where I'll be covering maths, chemistry, and physics topics and condensing them to short 5 to 10 minute videos for your leisure. In this video, we'll be going through Bivariate Data 1, and we'll be covering the topics of two-way frequency tables, row and column percentages, explanatory and response variables, scattergraphs, and also the reliability of predictions, so interpolation versus extrapolation. So before getting started, I highly recommend downloading the notes in the bio below so that you can annotate and follow through the video. Alrighty, so let's kick things off. Bivariate data. So essentially, it's just talking about two variables with a potential relationship or association. So for example, the consumption of a particular food, which could be variable 1, versus the death rates due to heart disease, which is variable 2. Bivariate data can be plotted in multiple ways, right? There are 3 ways that we'll go through in this video. Two-way frequency tables, row and column percentages, and also scatter graphs or scatter plots. So the first one we'll be going through is two-way frequency tables, row and column percentages as well. So let us suppose that the number of male and female members of two political parties, A and B, are given down below. Right, so as you can see that you've basically got the rows as the gender, so male or female, and the columns as the political parties, A and B, right? And you always have the totals at the bottom and at the sides, right? So essentially how you read this table is that whenever you sum up the values, it should equal to total. Doesn't matter if you're going by rows or by columns, it should equal to that total, right? But not diagonally, that doesn't work. So for example, party A, the total people in party, so for example, the total people in party A is 257, and it's comprised of 215 males and 42 females, right? Or for example, the total number of males in both political parties is 319. So having 215 in party A and 104 in party B. So these two-way frequency tables can be converted to percentages, see below. So we can always convert the raw data to the percentages on the exact same table, right? So what I mean by that is, for example, if you wanted to find the percentage of a male in party A, what you'd have to do is you'd have to go 215 divided by the total number of people from the data set, right? So 215 divided by 422 gives you 0.51. And then obviously if you want that as a percentage, it's just multiply that by 100 and you get 51%. And you do the exact same things for everything else, everything over the total of 422. Right? And very similarly, just like how we can sum up the values in the previous table, you can also do it for the percentages. So obviously if we want to find the total percentages of male, just add 51% from party A and 25% from party B, and you get 76% of males that make up the whole data set. All right. Furthermore, this can be visualized as a stacked column graph or a histogram, right? So how you read this stacked column graph is that it's out of 100%, right? So basically, if we're looking at party A, we can see the split between male and female. 84% of party A is made out of males, whereas 16% of party A is made out of females. And it's the same thing with party B, right? But it has to tally up to 100% because 100% makes up 100% of party A. So moving on, explanatory variable and response variables. So when investigating the relationships in bivariate data, once again, bivariate data, just two variables. The explanatory variable is the variable used to explain or predict a difference in the response variable, right? So the explanatory variable is also called the independent variable or predictor variable, whereas the response variable is also called the dependent variable or predicted variable. So for the above example where we had consumption of a particular food versus death rates due to heart disease, the consumption of foodstuff is the explanatory variable and the death rate is the response variable. So the foodstuff is the explanatory variable because it basically affects the outcome of the death rate, the response variable, right? So what you consume basically leads to the response variable. In this case, it's the death rate, right? So if you eat unhealthy foods, obviously there's a correlation. You're going to probably have a higher death rate, whereas if you eat your veggies and healthier foods, you probably have a lower death rate, right? So you can break down bivariate data into an explanatory variable and a response variable. So we did touch on row percentages or column percentages in the above. However, which one do we use when we answer questions? So follow this rule. If the explanatory variable uses the rows to show its different categories, use row percentages. So this is the percentages based on the row totals. However, if the explanatory variable uses the columns to show its different categories, use column percentages or the percentage based on the column totals. So if that meant nothing to you, went over your head, don't worry, we'll go for an example. So in modes of transport to work, consider whether gender explained any variation in the choice of mode of transport to work. So we're basically investigating to see if gender has any sway in the choice of mode of transport to work. So therefore, gender is the explanatory variable and mode of transport is the response variable. So show the different categories for the modes of transport, which is the response variable, for the row percentages for gender, explanatory variable. So in this case, because the question is specifically asking us to consider whether gender explained any variations in the choice of mode of transport, we basically nominate the gender variable as the x-axis. Basically what we do is we show the breakdown of mode of transport for each male and female as a percentage on a column graph, right? So ideally, if we're going back to the rules, if the explanatory variable uses the rows to show its different categories, use row percentages, so the percentages based on row totals. Since in this case that the explanatory variable uses the rows to show the different categories of modes of transport, we're basically using the row percentages to basically tabulate our column graph, our stacked column graph. Alrighty. So moving on to scattergraphs or scatterplots. So plotting your two variables, bivariate data, as points on an XY axis. I'm sure in some point in your life, you've probably done an XY axis and you plotted some data points before. So exact same thing, nominate. So rule of thumb is you always want to plot the explanatory variable on the x-axis and the response variable on the y-axis, right? That's a rule of thumb. If there is a trend, we can draw a straight line through it. Right, so that's also called a line of best fit, and fit a linear model to the situation. This linear line allows us to make predictions, but we'll get into that a bit later on. A couple of notes as well. The line of best fit is also called the trend line or least squares regression line. They all mean the same thing, so don't freak out. Your teacher might be partial to using one or the other. And also a really good tip when drawing a line of best fit is to use the edge of a ruler and try to distribute the number of points as evenly as possible on each side. The line of best fit does not necessarily have to go through the origin. So I see time and time again where students try to basically pivot or draw their line of best fit and make it go through the origin, but that's not necessarily. You might even get marked down if it's not fitted correctly. Cool. So there you go. That's your line of best fit. Bang. Obviously splits up the data points evenly as possible from left on the left-hand side to the right-hand side. So now moving on to the reliability of predictions, right? So talk about the following points for your graph if you guys want some marks. So these three things is what you have to talk about. Distribution. So the first one being distribution. Does the distribution on the scatter graph suggest using a linear model or perhaps another model? Such as quadratic, exponential, etc. Right? So for example, if this is what your data set looks like when you plot it, looks pretty random. It wouldn't make sense for you to put a line of best fit because there's really no trend. Whereas this one here seems like it's exponential and it doesn't make any sense if you put a linear line through it, right? And this one here actually looks like a pretty good trend and probably suitable to put a linear model. Second point is talk about the number of points, so sample size. So the more points you have on a scatter graph, the higher the confidence and the more reliable your linear data will be. So take, for example, this one here. Obviously, it looks pretty linear. It makes sense to put a linear model. However, let's just say you have less dots. Let's say you had 5 dots, right? It'd probably look pretty weak, right? And you can't say for certain that, it actually will look like this. So the more data set, so the larger your data set, the larger your sample size, the more confident you can be in your data. So the last one is actually really important. It's interpolation versus extrapolation. This might be the first time you guys are coming across these two terms, but you'll pick it up real quick and you'll start weaving it into your answers real easy as well to get some marks. So interpolation is basically data points that are within the given data set, right? So somewhere here. So making a projection using the linear model within the given points is more reliable as we already have the existing data. So for example, let's use this guy as an example. You've drawn a line of best fit. It looks like there's a bit of a trend as well. So it's good you draw a line of best fit. And then let's say, for example, the question becomes, what is the expected number of deaths per year due to heart rate disease for someone that consumes, let's just say 50 kilograms of food stuff per year, right? So all we have to do is go to 50, go up and see where it meets the line of best fit, and then go across and basically read whatever Y value that is. So that looks like it's 250 or 260, right? The fact that we're predicting this value using the given data points and it's within the given data points makes it more reliable. So you can say that that prediction is reliable because we're interpolating within the given data set. Whereas the opposite of that is extrapolation. So we're predicting outside the data set, right? So this is effectively making predictions outside the given points are likely to be less reliable as we do not know what the data looks like outside of the given points. It may deviate from the existing linear model, right? So what I mean by that is, let's say the question was, find the deaths due to heart disease, find the number of deaths due to heart disease per year for someone that consumes, let's say, 100 kilos of foodstuff per year, right? Because we don't have that data here, right? Our data set doesn't capture that. We're actually extrapolating because it's outside the given data set, right? And it's less reliable because at the end of the day, we don't have the data here, right? So meaning that this given data set might not actually follow the same trend, right? So potentially what could happen is this data set might actually, the data here could actually be somewhere here, making it more exponential. It wouldn't make sense for you to, therefore the prediction in which you're extrapolating is less reliable because you've assumed that the linear model holds consistently, right? Which may not be the case. Once again, interpolating is reliable because you're basically predicting within the given data sets, whereas extrapolating is unreliable because you're basically predicting outside that data set and we don't know what that data looks like. So if you're interpolating, it's basically within this range, right? The range of known values of explanatory variables. And then for example, the response variable predictions for A and B, it's still interpolating. So within this sort of these bounds, you're still interpolating. Let's say you wanted to find, if you wanted to predict the response variable for a value of C, which is outside the data set, see that? It's slightly outside the last point there, you'll be extrapolating, right? Once again, not very reliable. Cool. Well, that's it for this video. Hopefully you guys found it interesting, took something out of it. Once again, if you guys are just chasing after the notes, they're in the link in the bio below, and I'll catch you in the next one. Bye.